Welcome to the second part of Module 7 on genomic selection. And in this module, we're talking about the genomic selection schemes that can be used in plant breeding. We mentioned in the first module, half of this section of this module, that you could do rapid cycling. And now we're going to look at the second way to use genomic selection, and this is as a tool to help you with selection of lines from your field trials to advance the next stages of evaluations. And as mentioned before, these methods are not exclusive from one another. The goal of molecular plant breeding is really to broaden the top of your breeding funnel. The top represents lines that are untested, and therefore you have no phenotypic data on them, and so it makes it very impossible to select from them amongst them if you're doing only phenotypic selection. And the other goal we have is to make sure that when we get down to these advanced stages of phenotyping in the field, that we have the best germplasm possible going into them, and also that some of these trials, which are expensive to run, can be a bit smaller and of course more efficient. So we want to see how we can broaden the top of this breeding funnel by using genomic selection. But before we get to that, let's just look at how genomic selection can make you more efficient in your field selections. So we look at our breeding program, and you have different stages of testing. The first stage, you might have only 200 lines. You don't have much seed of them or many clones of them. So you do one rep, maybe 2 environments. That's 400 plots. Variety A exists in 2 of those plots. Second stage, you've narrowed it down now. You'll maybe only have 50 lines, but you're doing 2 reps, 4 environments, a total of 400 plots. And in stage 3, you may be down to 20 lines, 3 reps at each of 6 environments, 360 plots. So in this 1 year of testing with these 3 stages, you have 1,160 plots in 6 environments. But line A exists in just 2 of those 1,160 plots. So just a less than 1% of the total data from your field trials are used to select to determine whether line A is good or bad. What genomic selection can do is link data from all your plots and all environments to predict the value of line A. In other words, data from all 1,160 plots over multiple environments can now be used to help you predict the value of line A. And that might give you more robust selections than using just the phenotype data from stage 1 alone. And that genomic selection can link your current year season's data to data from past seasons, other tests to further enhance predictions. And it can also help you link your data to other programs. And the biggest benefit of this is to improve the selection accuracy of lines that are minimally phenotype, like lines in stage 1 or even stage 2. So here's a scheme that could allow you to do that. The germplasm is in your training population is your current breeding phenotyping program, and it's also your selection population. Rationale: phenotyping in early stages is sometimes inaccurate because of limited seed supplies and replications, and your parents that you use in your next cycle of breeding are often those lines that come out of stage 3 or 4 of testing, when robust phenotypes are established. These 2 factors result in low gain from selection due to inaccurate selections in stage 1, and also a long selection cycle by only using lines as parents after they've gone through stage 3 or 4 of testing, and this produces low gains per year. So here's a genomic selection scheme to try to remedy some of those problems. It starts with your basic breeding scheme, all the way through crossing, develop progeny, select the best progeny, put them in the first stage of yield testing or phenotyping, stage 2, stage 3, stage 4. You might also be running trials on cooperative germplasm tests. You may have also data from your commercial variety trials. All this data from all these lines can be used to build a genomic selection model. They are your training population. So all these lines are phenotyped, obviously. You also genotype all the lines, use that data to build a genomic selection model, and use the model to predict the value of all the lines in all trials. You then use the phenotypic data that you have and their estimated breeding values, and maybe even marker-assisted selection, to select the best ones. and the best ones are advanced to the next stages of testing. This would actually be repeated every year. Every year you have lines going in those trials that I call step, and they're identified as step number 2. And you do this every year. You start to build up a huge database of phenotypes and genotypes, and the data can be combined to help you make your predictions. Quite a few advantages to Scheme 1 over just phenotypic selection and other genomic selection schemes. First, it's simple. All it does is require you to genotype lines you're already phenotyping. And data from the multiple environment tests with multiple reps is used to help predict the value of lines in stage 1 or 2 of testing that are really not phenotyped that well. Lines from stage 1 and 2 can actually be selected and used as parents earlier than if you wait till stage 3 or 4 to use the lines as parents, as you have stronger predictions of them. Scheme 1 can be repeated each year, but only the new lines that entering your testing need to be genotyped. All the ones you genotyped from the previous year in advanced don't have to be regenotyped. Thus, your genotyping investment is really quite minimal. The scheme can be repeated each year, building your data sets up, and your data can be leveraged with cooperators. And Scheme A1, as I've called it, can increase your gain per year and gain from selection. Now let's look at a second scheme. We'll just add a little twist to Scheme number 1, and I call this Scheme A2. It's basically the same scheme as before, but now we're going to increase the size of our selection population. The germplasm in your current phenotyping program is again used as your training population and also as your selection population. But this time the selection population is supplemented with unphenotyped lines that are highly related to the lines in stage 1 of testing. The rationale, same as Scheme 1, but also we know that breeding is a numbers game. The more lines you evaluate, the better your chances are of finding a new variety. So your goal should always be to find ways to evaluate as many lines as possible. Breeding progress is often limited to the inability to phenotype a large population, and this limits your gains per year. So here is Scheme A2. These parts, Step 1, Step 2, and Step 3 are all the same as I showed in Scheme A1. The only difference is when you select these progeny that go into stage 1 of testing, from those same crosses you also select extra lines. These extra lines are not phenotyped, they're only going to be genotyped. So now you take all your phenotypic data and genotypic data from those lines, you build your genomic selection model. Your extra lines that you had set aside are going to be genotyped. Using that genomic selection model you just built in Step 3, you predict the value of each of these lines, each of your extra lines. And you advance the best of these extra lines to stage 2 of testing. And they could also be returned right back to the top and used as parents, bypassing basically all stages of phenotyping. And of course the best lines from these phenotype trials also get funneled down here into your next year of testing, just as these do. So basically, if you're only testing 150 lines in stage 1, but you genotyped an extra 200, now you basically have evaluated 350 lines per year. Not 150 in stage 1, 350. And this will greatly improve your odds of finding a new variety. And here's just an example of using Scheme A2, as I've called it, in maize. You have a heterotic group B. You cross 2 inbred lines from heterotic group B, develop inbreds. You take 50 of those, make them into test crosses, phenotype them, and also genotype the inbred lines themselves. You take 50 more inbred lines from that same cross and set them aside. And you do this for another cross and a third cross. Now you use data from the phenotyped individuals in the test crosses to build a genomic selection model, and you can actually build this model within each cross as long as you have put enough individuals in your test crossing to build an effective model. And people in the maize have suggested that 50 may actually be enough. So you build the model on this data, and use it to predict the value of these other 50 that were never phenotyped. So you do that, and it is possible that you can combine data from different crosses as well. In this case, this cross involved inbred line B2. This one involved the same one. So these inbreds and these inbreds are half sibs to one another, and data from those two crosses can be combined to help predict the value of the individuals that have been set aside. And again, in this scheme, you basically have doubled the size of your initial selection population by genotyping these 50 set-aside lines. So advantage of scheme A2, same as we listed for A1, but A2 can also now greatly expand the size of your selection population that you evaluate in those early stages. And of course, this is critical to breeding success. Genotyping these extra lines can actually be much cheaper than phenotyping them, especially when you consider phenotyping them for multiple traits. And due to their direct relationship of lines that are phenotyped in stage 1, the extra lines can actually be genotyped probably with low density markers. Then that could reduce your cost of genotyping these extra lines by 50% versus genotyping at a high density. The extra lines are highly related to the phenotype line, so we would predict that genomic selection accuracy should be quite high. And that is the end of this part of Module 7, and we'll continue it in the third part.